Hello everyone and welcome to the 57th lecture of the course Advanced Structural Analysis. We have briefly gone through the process of identifying the general stress strain relationship for the nonlinear material rule. We tried to break the system into the elastic and the plastic strain component, and somewhere we realized that the number of parameters which are based upon the elastic modulus, the yield value of the given system, the tangent modulus of the given system with respect to the nonlinear material rule, they become the important parameters to identify the general stress strain relationships for the given system. And as we go with the problems of the unloading, the specific cases that how the material is following the behavior with the load reversal, like the manner of the kinematic or the isotropic hardening, as well as the point from which the initial material is started to be unloaded, those all parameters also become important to be evaluated. The plastic strain component also remains one of the important aspect of the analysis, and that is what we have come up with some of the standard relations towards the end of the last lecture. Now, with this lecture we will try to extend the analysis to the general structural system. So, the understanding is that what we did earlier was defined with respect to a simple stress strain relationship for the given system. Now, as we move forward, we need to also know that the given expressions have to be utilized with respect to the general structural system, which means that the members like the frames, trusses or the beam members which are subjected to any kind of external loads, when they are subjected to the deformations, subsequently the members will deform to an extent that the internal stresses will exceed the original yield stress of the given system, and the material will start to show the nonlinear behavior in the given system. So, to keep the track of the given system, we need to correlate the external terms of the given system which are identified in terms of the joint loads or the joint displacements of the given problem with respect to the given system which are identified in the internal system of the given problem. So, these are the content which we will try to cover in this session. We will identify the general member stiffness, we will come up with the equilibrium relations for the incremental analysis, and then we will try to see that what are the specific incremental steps which we follow typically in the analysis by looking at specifically the errors which we need to correct in each step for the by doing the number of iterations. So, to start with, we have one system in which, say, we generally consider a simple truss members one of the member. As we have already done this part earlier in the geometrical stiffness formulation as well, we come up with the any member of the truss, we define that in the local coordinate it has some of the displacement parameters identified, and corresponding to the displacement parameters which are located in the system, the user can calculate what is the total change in length of the given member. Now, this change in length of the member can be defined if we have a large displacements also available, which means the geometrical nonlinear analysis, or in case the material is in case the displacements are not large, we can also follow the simple relationship with respect to the change in the length of the given system. So, the change in the length of the given member in a general form can be simply described by the small change taking place in the direction of at the node 2 of the given system in the member direction, minus the change taking place in the direction at the node 1 in the member along the member length. So, du2 minus du1 can ideally reflect the change in the length of the given member, provided we are not following a large displacement model of the given system. And this relationship can also be written in the same form the way we have identified the general relationship for the geometrically nonlinear problem, and we call now that this part of the given vector which has been defined is the general expression of the A parameter in the given system, and this vector which is defined with respect to the given displacement changes in the system can be described as the u bar in the given system. Now, only difference is this we have defined with respect to the change in the length. If you want to express it in terms of the strain parameter, the user can simply write it again as d upon L in the given system. So, the expression which have been defined over here, once they are divided by the L parameter, they typically reflect with the values of A in the given system. Now, the expression could either be defined in the member coordinates, which we have defined with respect to the A bar parameters of the given system, and as also we can convert these relationships in the global coordinates of the given system as well. So, as we already know now that how do we convert the general expressions with respect to the local to the global coordinates of the given system. What user can do at the beginning only, that instead of taking the displacement parameters in the local member coordinate, the user can define these values in the global coordinate as well, which are say u1, v1, u2 and v2 in the given system. So, knowing these values in the global coordinates, now the user can again come up with the general strain relationships which are located with respect to the transformed relationships, and those transformed relationships can also be applied to the general relationship of the A term in the given system, and that will give us the global coordinates of the given system. So, using this parameter, the internal strain of the given member is identified in terms of the nodal displacements of the given system. So, this is one of the aspects which we have already done in the previous part of the geometrical nonlinear analysis as well, and this steps remain similar because this is the same part where we are converting our nodal values to the internal member force component or the member strain components of the given system. Only difference is, it in most of the situations, if we are only going with the pure material nonlinear relations and not including the geometrical nonlinear part, so the user has to adopt only the given case which is identified here as a linear case. Whereas, in case if the user is willing to provide both the geometrical and the material nonlinearity in the system, the user has to come up with this parameter as a vector in the given system. We can also understand now that in the cases where say we go with the beam members or we go with the general aspect of the system where more than one strain parameter is available, the A becomes a general matrix in the given system. So, if you recall the discussions which we did with respect to the beam formulation, we came up with the two strain parameters, the regular strain and the rotation of the given system, and corresponding to that A became a parameter in which there were two individual rows identified for the given system. Now, moving forward, we have the general expressions which we can now define. We have said that the epsilon which is identified as the strain in the given system can now be represented in terms of the general local global displacement vectors of the given system. So, we identify the global displacement values of the system which have been located over here, and then we consider the transformation of the linear relationship with respect to the general alpha angle which the member is making with the horizontal axis x of the given global direction, and corresponding to that individual expressions appear with the values cosine of alpha, sin alpha with the minus sign, and the cos alpha, sin alpha with the positive sign in the given system. So, now this becomes a standard A value which we will be adopting in the global coordinates for the representation of the strain in a given system in terms of the nodal values of the displacements of the given system. So, this is something which we have formulated based upon the earlier discussions which we have done on the geometrical nonlinear analysis as well. So, I will suggest that those of you who are finding these expressions little difficult to follow should just go back to the discussions which we did on the geometrical nonlinear analysis, and there the these derivations will be clear with the much more clarity. Now, as a second step, we now need to define the relationships between the equilibrium of the given system. So, this is typically, if you recall, we define this as a kinematic relationship of the given system, which means that it is connecting the internal member strain with respect to the nodal displacement values of the given system. Now, in the same manner, I need to also connect the equilibrium in the given system also. So, when we think about the equilibrium, we understand that in the given member at the global coordinates we have some forces which are active, say the forces I can define. Again, I am following the similar notations which we have done in the geometrical nonlinear analysis. So, we have two of the nodes at which we have defined the forces P1 Q1 and P2 Q2, which are identified in the global directions of the given system. Now, using these forces which are also having the set of displacements available in the direction of these forces, the user can calculate the overall external work done by the given system, or at least the nodal work done by the given system, and that could be defined as the individual values of P1 U1 plus P2 U2, P3 U3 plus P4 U4 in the given system. This parameter, when if it is with respect to the same loading condition, will also be appearing with a factor of half in the given system. In case we consider that these displacements are the virtual or the small amount of displacements in the given system defined by d of u1, d of v1, d of u2 and d of v2 in the given system, we can directly write the relationship without the half factor as P1 d of U1 plus P2 d of U2 plus P3, sorry, I have to just modify it. So, this is P1 Q1, this is V1, this is P2 and this is U2 in the given system, and this is Q2 V2 in the given system. So, similarly P1 U1 Q1 V1 in the given system, and then P2 with respect to d of U2 component and Q2 with respect to d of V2 component in the given system. So, this could be defined as a small change in the external work done in the given system. So, we can consider that now this is the expression which is described with respect to the external work done or the work done by the nodal forces of the given system. In the similar manner, the internal system will also be having its own strain energy stored in the given system, and we realize that the internal system will be subjected to the stress and strain or the internal resistance of the given system, and corresponding to that now we can come up with that the internal strain, the strain energy of the system can be defined as the general amount of the stress in the given system into strain over the total volume integral. Now, of course, for this problem, for the present problem which is at hand, we have only one component of the stress which is the sigma x in the given system, because we consider that the system is only subjected to the normal stresses. Other than that, the amount of the shear stresses or the other component of the stress tensor are not present at this given situation. But still, to make the expression more generalized, we come up with the relationship where we consider that sigma transpose into epsilon dV in the given system, and this comes out as the general representation of the strain in the given system. Again, if we say that these are corresponding to each other, that the amount of the strain is directly attributed to the given change in the stress component of the given system. So, we can attribute it with the factor of half. Otherwise, if we say that small change in the strain is defined in the system and corresponding to that the value of the stress is identified. So, the user can also write this expression in this manner without using the factor of half. So, now as a expression we have defined the internal stored energy of the given system, the external work done by the given system, or the changes in the external internal stored energy and the external work done by the given system. We can now the equivalence of both of these parts to come up with the relationship between the general internal force relationship and the nodal force components of the given system. So, with this idea in mind, we can come up with the general understanding which comes out with the sigma transpose epsilon dV equal to P transpose U. So, I am writing over here now P transpose, which simply means that it can be adopted with respect to the all four components P1, Q1, P2 and Q2 in the given system. So, all the four component of the nodal force values have been identified in the vector form, and that is defined by the force vector P in the given system, and U also defines a vector form which is represented by the nodal displacements U1 V1, U2 V2 in the given system. Now, having this part clear with us, we can now identify the general relationship and try to consider that the sigma transpose epsilon we have already adopted in the previous part, that it is written in terms of the A and the displacement parameter of the given system. So, using this part, the user can write A into U dV volume integral equal to P transpose U in the given system. Now, we realize that in the given situation, when the U displacement is only defined with the nodal values, I can take it outside of the given system. So, it will not be going with the volume integral in the given point. So, that is where we can remove the U from both the sides of the given system, and what we get out of here at the final point is that P is equal to the A transpose sigma into dV in the given system, and this becomes now the standard expression which connects the nodal force vectors which are in the direction of the nodal displacements of the given system, and that is now defined in terms of the internal stress component of the given system. Now, this relationship we have earlier also defined for the general beam kind of a relationship. If you recall the truss kind of a member, we have also expressed this relationship in terms of P equal to A transpose S kind of a form, because we realize that the stress inside the given system remains more or stress inside a truss member remains constant. So, even if you do the integral of this given stress component, you end up with the given system which is the S, or which is the axial force of the given system. Now, the point is that the value which we have identified over here with respect to the general relationship typically connects the nodal values with respect to the internal stress components of the given system. And why it becomes important? Because the increments which the user are trying to make, those will be defined with the level of the external loads on the given system, whereas the material behavior which has been defined for the nonlinear response is defined at the level of the stress and strain relationship of the given system. So, once the user knows that internal stress of a given member is known to the user or is identified, the user now need to go back to the nodes of the given system and convert that into the equivalent forces which will be available at the nodes. And that is where we require this relationship to identify the connection between the nodal force values and the internal member stresses in the given system. So, we will try to utilize it in the subsequent part, but with this idea we come up with this relationship, and this is what has been defined over here, that P is equal to A transpose sigma into dV, and now we can say that sigma, which is say a function of the strain of the given system. So, this could be defined in this kind of a general form as well, and if we take a small change in the P parameter or the load parameter of the given system, it can be defined as A transpose the change in the sigma into dV of the given system. At this point, one has to be very careful with one point, that A, which has been defined over here, has been considered to be constant, which means that the user has already considered that the geometrical nonlinearity is not present in the given system, and that is why when we took the small change in the P parameter of the given system, we did not take any change in the A parameter of the given system. But you may go back to the discussions which we did in the geometrical nonlinearity of the given system. Once we know the relationship between the force and the internal stress component of the given system, to define the small changes in that, the incremental change, we not only go with the change on the stress component part, but also we do the change on the A component of the given system. So, we are not replicating that point again over here, but we believe that with the constant values of the A parameter which have been adopted over here, the expression will make sense for now. But in case if you are also adopting the geometrical nonlinearity in the given system, you have to adopt the variation with respect to the A parameter as well. Also, to make one clarification over here, the general expression of the A parameter which was defined in the previous relationship was defined with respect to the change in the length of the given system. So, d of E was defined with respect to A into d u parameter of the given system. So, I could say that this is A bar and this is u bar in the given system. So, change in length when we define, and now we are representing this with the strain parameter. So, there is a factor of the length parameter which has appeared in the given system, which was not earlier there. So, the idea of the A vector is still same, but only thing, the expression which we are using over here is also having a factor of L in the given system. So, one should not exactly copy it with respect to the same geometrical stiffness expression, but see that the utility that there we were defining the change in the length, and corresponding to that we express the term A of the given system, whereas here we are specifically interested to define the strain, which is the change in length per unit length of the given system, and that is why the denominator of L is also appearing in the given system. Okay. So, with this point, now we define that the general relationship between the force increment which will be available at the nodal points of the given system with respect to any change in the internal stress component is now known to the user. So, what user will do now, at any point of time, of course, at the external nodes we are trying to provide the load increments in the given system, that is how the simulation will start, but at the same time the tracking of the nonlinear relationship of the material rule will be done with the level of the stress increments in the given system. So, that is where we need to now make a balance between the external load increments as well as the internal stress related changes which are appearing in the given system. So, to see it in now more clear manner, we will go with the stress related increments in the given system. So, this is I think before that we will just see the final form. The d of P, the way we have defined over here, if I just convert d sigma, I can write it in terms of the same expression, that d sigma is equal to the amount of the material rule which is defined. Say if you have a simple material which is uniaxial tension system, so it comes out as the the elastic modulus of the given system into d epsilon in the given problem. But in case if we are using a generalized form where the sigma has more than one component and the strain also has more than one component, so we typically define as a d component in the given system, and as this is also being done with respect to a tangent modulus in the system, not the initial yield value of the system or the initial linear modulus of the given system. So, we provide this with the generalized form that either it is E of t or this is d of t of the given system. So, again if you want to recall that what is the d of t in the given system. So, we can just go back to the expression that which we define in the general beam formulation. We came up with something called as E A and E I as a flexural rigidity of the given system. So, this is representing that kind of a 2 cross 2 kind of a matrix. Only thing that instead of taking the value of E in the given system, we are taking the tangent modulus of the given system. So, with this idea we convert the d sigma in terms of dt into d epsilon in the given form, and that is where we just express that the expression which is defined over here d of p. So, if I just write it, d of p is equal to A transpose d sigma into dV in the given system. Now, we just modify it with respect to A transpose. D sigma is taken as dt times d epsilon into dV in the given system, and now we will just modify the value of d epsilon and realize that it is equal to A transpose dt A times d of u in the given system, and this is the volume integral. So, this is the nodal value of the given system. So, I can just take it outside the given system. So, using that I can get it as A transpose dt A overall volume integral, this is one part of the given system, into d of u in the given system. Now, what we realize that as a general relationship of the force and the displacement, this term has to be the tangent stiffness of the given system. So, this is what we were looking for, the general tangent stiffness of the given system. So, by using the general form of the system, we are able to now identify the tangent stiffness or the tangent modulus of the given system. Once we have this value, the stiffness value of the given system, now we can go ahead with the analysis of the general problem. So, we will now look at the stress increment in the given system. So, as we look at the given problem, we realize that we have identified this part as that once the kT value is known, user can go with the expression that kT into du equal to dp, where the dp is the increment provided with respect to the nodal loads of the given system. We will try to solve it for the d of u unknown parameter in the given system. Once the user obtains the d of u, or the user can calculate what is the relative change in the strain parameter of the given system. That can be easily done by utilizing the expression that d epsilon is equal to A times du in the given system, and once you get the epsilon d, the change in the strain increment, you can get the specific value of the strain in the given system by utilizing it, that if I define it at the node 1. So, I minus 1 into d epsilon in the given system. So, with this parameter the user is able to identify the strain at a new point on the given system. Of course, after that we have to again cross check whether any error in the evaluation are there, and we need to accordingly correct with the multiple iterations in the given system. But just this is the standard way in which we define the given procedure. Now, moving ahead with the stress increments in the given system. As I said that we are initially applying the loads which are with respect to the external loads or the joint loads of the given system. So, at any point if I say that this is one of the system, so there is only one load which is there is only one joint which is loaded with the external forces. So, these forces can be described as a simple vector form, and that is what is defined as a general P expression in the given system. Now, we need to come up with some values of the increments in the load values of the system, which means that we can start with saying that F1 and F2 initially are 0. Then we can come up with that both the values of the d of F1 and d of F2 at the first increment will be increased by some value of say 2 units, or it could be same also, or it could be different as well. As this increment will take place, we will come up with the new updated values of the forces. As a second increment, we will go with the system which is the d of F1 and d of F2 with the next increment, and we can go with the values say 3 units in the given system. Again, these could be same and these could be different as well, based upon that whether the loads which are say at the end, if I want to reach up to the load of 100 Newton in this direction, whereas this load is only 30 units. So, I can accordingly go with the larger increments in the F1 value, whereas the lower increments in the F2 value can be provided. So, with this idea in the given system, we can come up with the individual increments on the given system. So, with respect to the individual increments, the user is able to identify say the initial displacement value, which is say initial value at say some point 0, and corresponding to that the user is also able to identify the general strain parameter at that point. Now, beyond that we can come up with the simplistic analysis where based upon the epsilon I, the user can define the Kt, which is the tangent stiffness of the given system, and that tangent stiffness can be multiplied with respect to the displacement increment of the given system, which is unknown to us, equal to d of p. So, any load increment which the user is defining, say at the first step, has to be considered, and corresponding to that I will obtain the value of the tangent stiffness in the given system, and based upon that I will be able to evaluate the unknown value of the du in the given system. So, if we look at this part, we evaluate the k which is at u equal to u of I, say knowing the value at that particular point to us. This is being done for each member of the given system. So, for each of the member we will convert this stiffness which is defined in the local coordinates to the global coordinates of the given system. So, using the general transformation rule, we are able to convert the expressions from the local coordinate to the global coordinate of the given system. And finally, with this idea, we are able to express this relationship where d of ui, the increment in the displacement, can be calculated. Now, as we calculate this increment in the stress, we will be able to increment in the displacement value, we will be able to now calculate the updated change in the strain parameter as well, and that can be calculated by the simple expression which we have defined earlier, and based upon that the user can now calculate the strain expression at the new point epsilon I plus 1, and that could be defined as epsilon I plus d of epsilon I in the given system. So, knowing this new value of the strain parameter, the user can come up with the new updated value of the Kt at the given system, which is the next point of the given system, and then keep on incrementing the given system. Now, this is a system in which we did not do any iterations, we did not try to correct the given system, but now we can look at the general form and see that there are certain cases where the this kind of increment is much more helpful, like the case which is shown over here. In this case, if we have a constant value of the Et, the manner it is defined. So, at any point if the user is over here and the user defined the initial value of the say sigma n, for which the strain value is known to the user, corresponding to this given value, the Kt value can be defined, which is say at epsilon n of the given system. Once I know the given value of the epsilon n, corresponding to these given values of the sigma or the stress representations of the system, the user can come up with the individual values of the forces in the given system as well. So, the forces in the given members can also be calculated with respect to the given system, and with respect to the given system, now the simple load, any kind of a increment which is defined in the given stress component of the system, if we define this increment value say d sigma on the given system. So, we realize that from this point the system will move to a new point which is which is sigma of n plus 1, and now this new point will be located with this constant slope. So, the system will be able to track the next point very appropriately, because the slope of the given system is remaining constant and the user has identified the tangent modulus, the Et value, at the same position of the given system. So, with respect to the defined tangent modulus, user can simply calculate that d sigma is equal to, which is this increment in the system, is equal to Et, which is the tangent modulus of the given system, into d epsilon, and knowing the value of the increment which has been say provided by the user can be able to calculate the value of the strain increment in the given system. So, I will call that this is d epsilon n in the given system. So, once the d epsilon n is calculated, user can calculate the epsilon n plus 1, which is equal to epsilon of f n plus d epsilon n in the given system. So, knowing the next point on the given system, once we evaluate the next point on the given system, the simple point is also attributed by the same value of the stress. So, the stress at the point n plus 1 is also obtained, which is same as sigma n plus d sigma n of the given system, and now this is the next point which has been located in the system. If user want to go with the next level of increment, user can go with say further increment in the given system. So, I can call it that this is d sigma 1 and this is say now the d sigma 2 in the given problem, and as the elastic modulus or the tangent modulus of the system is constant, user does not require any corrections in the subsequent steps of the given stress increment in the given system. So, we are already trying to write something which was earlier done with respect to the load increment, but we must realize that any part of the load increment, as we already shown here, is also trying to generate the amount of the strain changes in the given system, and this strain change can be associated with the amount of the stress increment in the given system. So, what we are trying to define now, that to track the material relationship, the stress increment which is identified in the given system is being referenced, and corresponding to that we are trying to see that whether the corresponding stress increment which is being provided will require any kind of corrections, or the user can simply go ahead with the answers which are being obtained by the simple algorithms. With this part we stop over here. We have briefly discussed that what are the different ways in which the stress increments can be provided to the given system. Now we will briefly try to see some problems so that we can understand it in a better way. Thank you everyone.